in Microsoft Teams. Welcome to class. Today we are moving into chapter 7. Chapter 7s are dealing specifically with alkenes. All right, I think everyone is comfortable with alkenes. These are carbon or organic molecules that have a carbon-carbon double bond. Right. So chapter 7 is really dealing with some of the unique features of alkenes, but most importantly is really dealing with the elimination reaction. Okay, so let's kind of really quickly. I can take an alkyl halide. All right, I'll write this down here. All right, and this is no different than the alkyl halides that we used in chapter 6. Right. However, instead of doing a substitution now where a nucleophile comes in and interacts with our alkyl halide, now we're going to have a base. All right. So whenever an alkyl halide sees a base, I'm going to facilitate a elimination process. All right. So what happens now in my elimination is that I gain a carbon-carbon double bond, and I'll lose my leaving group X, but I'm also going to lose an H off of my molecule.
Dr. Cooper, are you having in-class today?
No, I don't have anybody. I don't have an in-class today.
Okay, I just came to math and science. I wasn't sure.
Oh, you came to in-class today?
I'm standing outside the door.
Oh, yeah. I haven't had anybody for the last 2 weeks, so I stopped going there. Um, You see, I can set you up. You want to come down to my office? I can project my screen in 228 or
Okay, here I come.
220 something. This is the room right across my office. Okay, I'll see you shortly. All right, everyone that's in Teams, give me 1 second. I just need to set my projector up. I'll keep running my mouth in between here. All right. So again, if I have an alkyl halide in the presence of a base, now I'm going to lose an H in my halide, and then I'm going to gain a carbon-carbon double bond. Right. This process is known as elimination. All right. So we're going to break this down in more detail shortly. Okay, and for all students that are currently in Microsoft Teams, just give me a few seconds. I just need to set up my overhead projector. Okay, you're more welcome to grab a chair. All right, just give me 5 minutes for you guys.
And some of them need to be there.
It's not that big of All right, just a few more seconds, teams. Almost there. Okay, I'm can you see okay? All right, it's gonna be, see if I can make this a little smaller. All right, in teams, give me a few more seconds. I'm almost there. I just wanted to make this a bit smaller. Yeah, that's it. Okay, it's not gonna be perfect. This door. Okay, I'm gonna reshare my screen here. I'm going to make sure I project the right screen. Okay, this is gonna be a bit tough on my end now. Hmm. Okay, Miss Doe, I'm gonna have you do this. All right, the only way I can use that second screen is I have to see it too off of the projector. Would you mind just? Yeah, you can sit. You actually sit in my office. All right, teens, give me 1 sec. All right, I should have already let people in. I don't see anybody that needs to be put in. I'll look one more time. Okay, my second screen. Okay, let's do a test of screens here. Okay, if you can see the screen and hear my voice, could you just raise your hand for me? Okay, so it looks like most people have their hands raised. I'm so sorry, Ms. Dorr. I didn't have things set up for in class today, so I deeply apologize but hopefully this could somewhat help. All right, the recording is still on, so hopefully you guys will be able to, if needed, take a look at this recording. All right, so there's one big important thing here that I want to make sure everyone is looking at. All right, I'm gonna have to minimize this now to be able to work with this program. All right, the main difference in determining if something is a elimination or a substitution is the reagent over the arrow here. All right, bases are going to facilitate, are going to encourage, I guess you would say here, elimination reaction. All right, and that should be something that's common knowledge to us now as a class. Why do you feel like, how do I know that the base is going to facilitate an elimination process? Hopefully you guys can see from the fact that bases are going to extract a hydrogen, right? If we had to define bases, you guys know that a brine state base is a substance that removes a proton, right? So for this process to occur, I need to move a proton, all right? Keep in mind, a proton is not a hydride, right? Or is not a hydrogen. So an extracting hydrogen is a radical, an hydrogen atom with one electron. Extracting a hydride or moving a hydride moves an H with two electrons. If a base is present, it's going to remove a proton. So that means it's going to remove a hydrogen without any electrons. So the electrons that are present are going to form this double bond while it kicks off the leaving group, right? So this is how we get that elimination process. All right, conveniently, eliminations can occur in two ways, right? So there's two ways to do elimination, or two mechanism types, I guess you would say. All right, the first type is known as the E2 type. This is very similar to the SN2 type. This is why we teach these two things, or this is why I teach these two chapters together. All right, the same information that you would need for the SN1, I'm sorry, for the SN2, it's going to be very helpful for the SN, or for the E2. So what does that mean? E2 processes, if it comes down to alkyl halide, right? Just like the SN2, they're going to prefer primary. I'm not going to be able to get all my characters. Let me see. Okay. Secondary. Actually, it doesn't matter necessarily if it's tertiary too. And some tertiaries can react here as well, right? Not all the time, so it doesn't matter as much, as well as any allylic or benzylic system. All right. Here, the base preferably needs to be strong. Okay. And most importantly, the solvent for E2 processes needs to be polar aprotic. Right? Pretty much our to the mechanism type is that the solvent is polar aprotic. Okay. All right. Sorry, I'm going to be a little bit slower
Dr.
today.
Hoover, some people need to be let in.
Okay. I let everyone in that buzzed on my side. I don't see anybody that's not in. Can you tell me who's not in?
I don't know their name.
Okay. Somebody just buzzed right now, but I already let in a large group of people. Okay, I would say this for attendance to class. If you can make it to class by 11 o'clock, that's going to make your life a little bit easier. While I'm lecturing, it's almost mission impossible to kind of do both. I try my best, but I'm not going to be as effective doing both. All right, I'm going to be a little bit slower than usual today because I have to look at this from a different screen. So it's completely awkward for me to do this. So this kind of hang in there with me today. All right, but for the E2 process, I need primary and secondary alkyl halides. I need a strong base, and I need polar and protic solvents. So let's take a look at the mechanism for an E2 process. All right, I'm going to try to use that same example to have on board here. I'm going to have a bromine here. All right, so the first step, or the steps that happen here, is that I need a base. Oh boy, I can't see it. All right, in this case here, I'm going to use lithium hydroxide. Right. Keep in mind that lithium hydroxide is ionic, so the lithium is going to have a plus, and the hydroxide anion is going to have a minus charge, right? Okay. So one lone pair from the hydroxide anion is going to remove a proton, all right, while I break the chemical bond between the carbon and the H here. That's going to kick off my leaving group. See if I get a better arrow for that. So just like the SN2 process, this all occurs in one step. Right? So this is a concerted process, but now there are 3 arrows to keep track of. Right? My base extracts a hydrogen, extracts a proton. The corresponding electrons are going to form a double bond while kicking off my leaving group. Okay. So now my product is going to look like this right here. And if you want to see the byproducts, you're going to form HBr, and you're also going to form H2O. Lithium is going to be interacting with any of the corresponding solvents here. All right, so somebody asked about what's going on with lithium. I'm not sure the steps here, but the first 2 components is this plus H2O. Right. And if you continue the process, all right, HBr will start to fall off instead of the lithium bromide. But this is probably the easier version for you guys to see, so I'm sorry. Right, the oxygen is going to pick up an H here, so I'm forming water, and lithium and bromide is going to form together to form LBI. All right, but I want to make sure you guys are concerned with this, right? And I guess, everyone is different, and that's fine. I'm an organic chemist, so these byproducts are insignificant to me. As long as you can see that the double bond forms and you kick off the leaving group, you're going to leave an H, that's perfectly fine. These byproducts forms in a lot of different ways, right? That's why I don't want you guys to get too concerned with that process right now. Right? But if you're going to be a chemical engineer, yeah, that's something very important to think of, these byproducts, to think about all those potential products. All right, so let's go ahead and write this down as in order of steps to make sure everyone is comfortable with this so far. So step 1 in this process, oh boy, it's going to be too hard to do. All right, step 1 is where I have my base. All right, I'm going to remove proton. All right, please keep in mind what a proton is. Step 2 of this process is where proton is. I have to write this in. The electrons shared between proton and carbon are used to form a double Sorry, I'm trying to look at this on 2 screens here. And in step 3 here, the leaving group leaves with 2 electrons. All right, so let's try to review really quickly before I move into the other type of elimination. All right, I want to make sure you guys know that these are not necessarily steps, but this is the best way that I can try to explain the arrows, all right? So maybe I shouldn't say 1, I'll call this 1B and 1C, all right? These are all happening at the same time. So this is a 1-step process. All bond forming and breaking steps occur. All right, so that's very important to keep in mind. That this is all one step. All bonds forming and breaking steps occur at once. All right, there's not necessarily one thing that happens, then something else has to happen. Right? That's what it means to be kind of in a E2 process. And again, E2, I didn't define that, is a bimolecular elimination. So what does that mean? You guys know what that means in some type of way. Anybody help me out? What is that really trying to say? So the rate, the kinetics is by equilibrium constant. Yeah. Good, very good. So Ms. Dory had it right. She told me that the rate of these type of reactions depends on both components, right? That's why we call it a bimolecular reaction. In this case here, a bimolecular elimination. Depending on both the concentration of the alkyl halide and the concentration of the base. So this is all one step. All right, so again, and this is where your strength of mechanisms are very important for this class. This is what I'm trying to assess. Do you understand what these arrows are trying to show, right? So it's saying that the lone pairs on the base and this component, the basic nitrogen, the oxygen is the basic atom here. It has 3 sets of lone pairs. It's a form of negative charge. It's going to take 2 of its electrons and grab a proton. So that means it's making a bond with that. This is how we get water. right? OH, and it gets another H. That's going to be H2O, right? Those two electrons are going to grab the proton, but the two electrons that was in this bond did not leave. Instead, they're going to collapse down to form a double bond, right? And it's set up to do this because all I need to do to form a double bond here is lose one of my bonds, and I'm going to lose a bond to bromine, right? So my bromine is going to leave off. So now I form lithium bromide, a carbon-carbon double bond in water as a byproduct, right? So be comfortable with drawing these arrows if you guys don't mind. Okay, what is the opposite you think of this process? E1, right? And this is going to be very similar to which process? Yeah, to the SN1 process. All right, can you guys still hear me in Teams? Say yes or no?
Yes.
Okay, good. I'm going to scroll this down. All right, so the alkyl halides here are preferably tertiary. Secondary, primaries could work with a rearrangement. And it doesn't matter if it's benzylic or allylic, those systems are fine here. Strong bases are cool, but also they can do with these weak to mild bases as well. They're potentially okay. But most importantly, my solvent here has to be polar protic. So there's something I need to be aware of, right? And I need to be aware of carbon cation rearrangements. All right, so let's look at the steps of this process. I'm going to use the same alkyl halide here. Right. I apologize. I didn't put a base. I didn't put a solvent here. We can use DMSO. It's a really good solvent, but I hate that solvent too. I don't like it because it's high, very high boiling, but it's all right. Okay, let's go ahead and grab this information. Help myself out a little bit. Coming out here. All right, this time I'm going to use a solvent called H2O. You guys know what that is. That's just water. Okay, so my first step is where now my base is still going to pick up a, sorry, I can't see that currently in my current way of opposite direction. All right, my first step is that my base is going to grab a proton. Okay, is that right? All right, you know what? You guys don't know that yet. I'm sorry. All right, this is not right. What's the first step that should happen? Yes, every E1 process has my leaving group leaving first. Right. I'm so sorry you guys didn't do this yet. All right, so leaving group leaves, and I'm going to form with intermediate here. I'm going to form a carbon cation. All right, so my carbon cation. If you had to classify this carbon cation, you guys would tell me which type. Secondary. Yeah, this is secondary. Okay. Is there any potential rearrangements for this one? All right, somebody says yes. Right, I will beware, right? So there are neighboring hydrides on both of these carbons, right? So again, to check for rearrangements, I need to only look one carbon over. That carbon or that carbon. There's two hydrides here, and there's two hydrides here. If I do a hydride shift from here to there, right? Or from there to there, I go from something that's secondary to something that's also wet. Secondary. So in these cases here, the rearrangement, is it productive?
No.
It's not.
You can move to the left with your tertiary.
None of these would be tertiary if you do a hydrogen shift. This one and that one. These are still hydrogens here. It's hydrogen here.
Okay, can you explain why I think you to the left with your tertiary?
Yeah, if you do a hydrogen shift, the carbon cation will go there. There's one carbon attached to it, and there's another carbon. So that'll just be secondary.
Oh, okay. Okay, it's not a carbon. That's H not a carbon. So that's why.
Yeah, sure. Okay, good. So there's no productive rearrangements here. Even though I drew this HN, that's just for the mechanism, right? But there's no potential rearrangement that could occur. All right. So actually, you know what? To be fair, I'm gonna erase this, but I'm gonna draw both H's in. All right. So step one here is I need to eliminate my leaving group. So step one. All right, my leaving group needs to generate a carbon. I think everyone is getting comfortable with that stuff. All right, if there is a rearrangement could occur. All right. But my second step now is now my base can participate. All right, I'm just going to draw OH minus here for you guys. I'm going to throw people off like what happened to the lithium. I'll just draw this down here. Okay. Also here, as a byproduct, I generated lithium bromide already. All right, again, that's not important to see, but knocking out the leaving group gave me LiBr plus that. Now I have OH minus as a free anion, and it's going to pull the proton. In this case here, it doesn't matter which one it pulls, right? I need to pull a proton on a neighboring carbon. I can pull that one, or I can pull this one. All right, these two hydrogens are identical or equivalent, if you're going to say. So step two here, and we're going to talk more about how to know which proton to choose, but if they're are equivalent, it doesn't matter. You pull either or will give you the same answer. All right, so now the base going, get the font right here so I can type everything out. All right, so the base moves proton from a neighboring carbon to the carbon cation. And the base above both hydrogens are equivalent, identical. All right, so this second line is setting you up for something. Sometimes it does matter which hydrogen you choose. Right now, they're both equivalent, so it doesn't really matter. Let's make that a topic. Okay, I cannot see why that's not working. Okay, I'll fix this later when I send this to you guys. I won't eat up too much time. All right, so it doesn't matter which one of these arrows. I'm gonna make one of these gray so I don't confuse anyone. All right, in the mechanism, you don't draw both of those, you just choose one. Okay, so just choose one of these arrows, right? But you could have went this way as well. All right, I'm gonna pull this proton. All right, but keep in mind, doing so is gonna allow me to form a double bond. All right, so there's two arrows in this second step. All right. All right, the electrons, so the two electrons bond with carbon, form a double bond with the carbon cation. All right, this is what's driving this step. This carbon cation is like, I don't have enough bonds. All right, electrons cannot jump from this carbon to that carbon, but they can be what between the two carbons? Shared, right? All right, electrons can't jump from one carbon to the other, but I can share my electrons. I'm going to share my electrons in a bond. So we already have a single bond, but you need some more sharing, right? So I'm going to make a what? A double bond to keep that sharing going. All right, so now I generate this compound plus your H2O. Okay. What's going on today? Okay, good. Any questions currently? I should have drawn it up, but all right. So if I look at the two processes here, right, it looks like they give the same product. In a lot of cases, sometimes they do. This is the same molecule. We'll talk about how I know that shortly when we cover naming, right? But these two compounds are exactly the same, right? But they're formed through two different mechanisms. So I'm gonna make sure I put this down here for E2 processes down here. Let me copy this. Okay, so these steps here are all unimolecular. All right, so that means that the kinetics of this reaction depends solely upon just the concentration of the alkyl halide, all right? Adding more base does not speed up this reaction, all right? And these are two-step processes, right? First step, that generate carbon cation or the leaving group leaves. The second step is the base moves proton and double bond Good. Sorry, this screen I'm looking at is kind of weird to look at. Okay, good. So the take-home point now is just to get familiar with the mechanism, right? And the only thing that's a little bit different from what we were doing before, typically with nucleophiles, I just attack the carbon that had the leaving group and things leave. But with eliminations, I need to have a step where the base is extracting or removing a proton, right? So that step has to be now drawn in as well. So let's start talking about things when the two hydrogens are not identical, right? So this leads us first to think about the stability of alkene. So we need to kind of think about this first, and then we can think about another rule that will pop up. All right, so the rule here is that the more substituted alkene, the more stable. That's going to be very important when we start thinking about major products here. All right, the more stable you are, the more substituted you are, the more stable. All right, so the rule here is that tetra substituted alkenes are more stable than tri substituted, are more stable than di substituted. And there's two types in di. It's going to be trans versus the cis. And then these are more substituted than mono. What happened to my mouse here? Okay. All right, let's take a look at these really quickly. Let's see if I can bring that down. Okay, so if I have a double bond, sorry, give me a sec, get my settings right. And I have all carbons, all right, and R just means carbons here. Right? I have 4 carbons on my double bond. Sorry, it won't let me select these easily. Right, this is known as a tetra substituted alkene. Okay, next is that I have a double bond only has 3 groups attached. All right, there's going to be an H here, right? This one is going to be known as a tri-substituted. Right? I could do the same thing with a, oh boy, this is not, okay, where did they go? Yep, that's fine. I'll take care of it. Thank you, Ms. Dora. All right, I know I'm running a little bit over. I'm almost done. All All right, in this case here now, I have a dive substituted because I only have 2 R groups attached to my ring, right? And you can also indirectly count the number of carbons, right? So I have a dive substituted class, right here. All right, I have my 2 R groups on opposite sides of one another. This is known as trans, right? And trans is a little bit more stable, or it's more stable than my cis, right? And how do I know this is cis? My 2 R groups are on what?
They're on the same side.
Same side, that's right. So out of the di-substituted class, trans is more stable than the cis. And then lastly, copy this, okay. Paste this, paste right there. It is my mono-substituted system here, right? And mono only has 1 R group here, right? So I'm hoping everyone's getting comfortable with the stability of alkenes, right? And the reason why we need to know this because up top here is going to influence how we choose the hydrogen to pull to generate a final product. All right, so before we end, I'm going to go ahead and end with this rule that we'll break down more next class. All right, definitely got to speed up next time. Is the Zeta rule. All right, Zeta rule says this. I'm going to generate a more stable alkene, right? That's going to always be the major product. All right, so there's some information that comes indirectly out of here, and this is remove the proton from the carbon with the fewest number of hydrogens, right? So this becomes very important very soon here, is that we have to make a choice on which hydrogen to pull, right? And we're going to use Zeta's rule to be able to choose the right one. So we need to remove the proton from the carbon with the fewest number of hydrogens. Let's do one question and we'll end today. Right? So I got this compound here. Come out of this. I can't see anything today. All right, I'm going to use my favorite base, lithium hydroxide here. I'm going to operate it in DMSO. All right, so I need to keep track of which potential hydrogen I can pull for the product. So I'm going to go ahead and draw in some hydrogens here. Neighboring the carbon that had the Liebman group, right? Sorry. All right, so now mentally I need to make a choice. So we learned that I take a base, I form a double bond, and I kick off the Liebman group. But which side do I pull the H from, right? So if I look at my right-hand side, I have how many hydrogens here? A total of 2, right? Is everybody comfortable with that? All right, there's 2 hydrogens on this side. And on my left-hand side, how many potential hydrogens are present? 3 hydrogens, right? Okay, good. I'm hoping everyone is still with me here. Right 2, left 3. So let's see what happens. If I make a double bond on the right-hand side, I'll generate this. All right. I'll call this the the 3H side. Okay. Versus generating a double bond at the 2 hydrogen side, this compound. And we'll call that 2H side, right? So can you guys tell me, out of these 2 potential products, which one is the most stable product? The left or the right?
The one on the right.
Yeah, the one on the right, right? Very good. How do I know that? So this right here is the major product. All right, how did I know it's major? First of all, you guys can tell me what type of substitution of the alkene it is, right? This alkene is known as which type? This is a tetra, tri, di, or mono substituted alkene. This is di substituted, right? And it falls within the trans family, right? So this is a di substituted alkene. What about the other one, the first one drawn for the 3H side?
I have a question.
Yep, go ahead.
How did you know that it was trans?
Yeah, because the 2 groups are opposite each other, right? This one's on the top face. Can you see this imaginary line right here? Maybe that helps a little bit. All right, so you want to look at the double bond and try to determine the orientation of sustenance. Three, send that to the back. All right, so those are the only R groups attached to double bond, right? So if I look at the double bond, this methyl will be kind of considered on the top face, if you want to say this, or you can even say it's kind of on the right side. And this one over here is on the bottom face of this, right? To be cis, they would have been both on the same side of this line, right? So if I drew a line up this way and had a methyl group, they're on the same face. Or if I drew a this group down this way, they're on the same side of that line, right? Because they're on opposite sides of that symmetry line, they're corresponding to trans. Does that help? We're going to do some more work with cis and trans, but I'm hoping that these are straightforward right now. If they're opposite to each other across a double bond, they're trans. They're on the same side of the cis. They're not on the same side here, so they're trans each other. Okay, good. Over here, what type of alkene do I have?
Is that secondary?
Well, no, we don't classify alkenes as primary, secondary. But typically you would say tetra-substituted, tri, di, or mono-substituted alkene, right? So what type of alkene will you say here? There's only one carbon hanging off that double bond, right? So this would be a mono-substituted alkene. All right, so out of the two, right, we know that di-substituted alkenes are more stable than the mono, right? So we know that this is the major product here, or this is the more stable product. And Zeta rule tells us that we can generate this one by pulling from the side that had the fewest hydrogens. Okay? So we're going to try to talk more about this next class. We're also going to talk more about alkenes and the geometry. There's some stereochemistry that we have to use, and you guys will learn the easy. There's 2 new letters that we use for stereochemistry at double bonds. All right. So good. I will give this to you guys, and we'll try to keep working on reactions next class. All right. Thank you for hanging in there. I'm so sorry today was a little different. I wasn't prepared to teach in person, so I had everything in my office. So I had to try to use the overhead projector today, or use my projector to do that. Stop the recording.